Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing Chapter 8 on correlation and regression, and continuing by talking about simple linear regression, modeling data with a straight line. So far in this chapter, we've talked about the correlation coefficient, doing hypothesis tests, computing the logarithm of the x or y variable in order to take a curved relationship and make it linear. And in this video, we'll focus on the case where we already have data that looks pretty much like a straight line would model it, and we're going to develop that line using least squares. So let's start with some definitions. So the y variable on the vertical axis we will call the response variable. That's the variable effectively that we want to be able to predict conditional on the x variable, which has many names, sometimes the predictor variable, sometimes the independent variable, sometimes y is called the dependent variable. I will often say predictor in class. And we want to develop an equation where we can predict y from x. And note that the variables aren't treated symmetrically in regression, that choosing to model y conditional on x, you will get a different line in the plane than if you were to switch their roles. So there is some thinking that needs to be put into place before you perform linear regression. Just as an aside, in correlation, the directionality didn't matter, but here in linear regression, it does. So let's go back to algebra and think about what an equation for a line looks like. Here's the equation that we will use. We'll have our response variable y, we'll have our predictor x, beta naught will be the y-intercept. Effectively, if you set x equal to 0, this term goes away and you get y equals beta naught. So that's the y-intercept. And then beta 1 is the slope associated with x. So for every unit increase of x, we expect y to increase by beta 1. That's the interpretation. And that's important for you to know. So let's scroll down and take a look at two equations. Here is one equation. All right, so in this case, if we set x equal to 0, then y equals 5. So that is when x equals 0, y equals 5. That's the y-intercept. And then we have 3 times x. That is, for every unit increase in x, we expect y to increase by 3 units. Nice. Another example, y equals 7 minus 2. Set x equal to 0, then y equals 7. So x equals 0, y equals 7. That is the y-intercept. And then the coefficient in front of x is minus 2. So for every unit increase in x, we expect y to decrease by 2 units. So if I use language like we expect for every unit increase in x for y to increase by negative 2, that's the same as decreasing by 2. So I may interchange those ways of saying, discussing the slope. So when you've got random data, how do you determine what the best line is? And there's lots of statistical theory for this, which you would see in a linear models class. And there are special cases that reduce to using least squares to find that best line. So we need to define squares, and we need to define least, and we need to determine what we're squaring. All right. So we've got a set of data, xi and yi pairs, and we've plotted our data, and we're going to determine what that linear equation is that best summarizes the data. All right, let me find. All right, I'm going to page up a little bit. All right, let's start with this equation. Y equals beta naught plus beta 1 x So what we'd like is to find beta naught and beta 1. Those are our unknown parameters that we're estimating. So one way to get those is by minimizing the squared errors. So I'm going to show you a picture of that in a second. But one thing you can do to this equation is take this part on the right and subtract it from both sides. So then you'd get y minus the beta naught plus beta 1x equals 0 if you subtracted that from both sides, right? So I'm going to scroll down and we're going to see that right here. yi minus beta naught plus beta 1 xi, just that part, equals 0. Now we won't have it equal 0 unless the yi's and the xi's fall on a perfect line. If they don't fall on a perfect line, then this line won't actually describe the data perfectly. So let me scroll down. I think I've got a picture here. Here's a plot of 5 data points. I'm going to zoom in just a little bit so we can see them a little better. On the horizontal axis we have x, we have on the y on the vertical axis, and we've got 5 points. 1, 2, 3, 4, 5. And we want to find the regression line, the line that's drawn here, such that we minimize the squared errors. All right, so what are the errors? The errors, or residuals, are the unexplained difference between what we observed and what would be predicted from the line. So these vertical distances are the residuals. The one I'm pointing at right now is about 1 unit tall. So we've got about 1 on this one. On the far left, maybe it's 0.1. In the center, maybe about a half, and then about 1, and then maybe 3/4. And you can imagine if you move this line so it's in some other location, that our residuals would look different. Certainly we would find larger residuals if we had different line. In fact, move the line way up here, and all the residuals are huge because there are big distances between the points. Okay, so I'm scrolling up, I'm zooming out. So we want to minimize this equation, the distance between what we observe and then what we expect from the regression line. So the beta naught plus beta 1x defines the regression line, and the yi describes the actual data values. And we're going to subtract what we observe and what the line predicts. We're going to square those values, and then we're going to add them up for all the observations and see what this equation gets to us. And beta naught and beta 1 will then be determined as the values that minimize this whole expression. All right. We have nice closed formulas for estimating beta naught and beta 1, and the computer's going to do it for us. Okay, and typically it's going to give us, typically your eyeball fit for the data is going to be somewhat pretty close as going through the heart of the data. All right. So I do have equations here. If we want to estimate beta naught and beta 1 with B naught, and B1, just like we estimate often the Greek letter for the parameter with a Roman letter for the statistic, then you can calculate B naught as this, where you've already solved for B1 here, which is related to the covariance and the variance of x. All right. A couple points I make are that the slope of the regression line, B1 or beta 1, will have the same sign as correlation. So if it's positive, they'll either both be positive or both be negative. So let's fit this data, or fit our model equation for the blood loss versus weight relationship in the thyroid data. So we're going to fit a linear model using the thyroid data. Blood loss is our y variable, and weight is our x variable. This is the relationship that had higher correlation in in previous video. I'm going to put that into a linear model object, and my convention for labeling my linear model objects are to have lm dot, and then name the variables. And depending on how many variables I have will depend on how verbose I end up being. But this tells me that I've fit a model with blood or blood loss as the y variable and weight as the x variable. All right, so I'm going to output that to the screen. It tells me what I use to generate this formula, and then here's beta naught, the estimate, and the estimate for beta 1, the intercept and the slope. You can plug these in to a regression equation and then plot it. Below, which we'll talk about a little bit later, if we ask for a summary of this, we get a little bit more information. We have the 5-number summary of the residuals, and this largely is to indicate whether the residuals seem somewhat symmetric and possibly normal from these 5 numbers. Furthermore, we have a coefficient table which we'll look at in much more detail, but notice in the estimate column we have the intercept, 552, which we saw above, and then the weight, negative 1.3, as the slope. And then to the right, we have other quantities for those estimates, including a t-test and a p-value for whether those values equal 0 or not. Effectively, we're most interested to know whether the slope related to weight is different from 0. So do we have a negative slope or a positive slope? And there's some other information at the bottom which we will learn about as well. Let's look at a plot of our data with a regression line. We've seen this code before. This is using ggplot to map x and y, weight and blood loss to x and y. I'm going to plot the points, and then I'm going to use geom-smooth to plot a straight linear model regression line. And I'm also showing you, using the base graphics of R, how to plot and put the regression line on top. So here's those two plots side by side. This is the same plot we saw earlier in the scatter plot matrix in a previous video. We've got blood loss on the y-axis, weight on the x-axis, and we see the regression line going through the heart of the data. And to my eye, this regression line possibly describes the data pretty well. You sort of have to think a bit about maybe this extreme observation and this observation down here look sort of a little bit different than the other 6 values. And then you also want to consider, secondly, that you have a pretty small data set, and perhaps this is just standard variability. It's hard to make very strong conclusions based on such small sample sizes. On the right is what the plot looks like from the base graphics of R. I think they are equally informative. All right, let's interpret this regression line. So our fitted line is y hat. The hat means that we're making predictions for y. And for a given value of x, it's 552. So the blood loss is 552 minus 1.3x. So for each kilogram of weight of the patient, we predict that there'll be a 1.3 decrease in the milliliters of blood loss. And so a follow-up question, what is the expected blood loss for a person who doesn't weigh anything? I should have asked this question first. How should you interpret 552? Okay, so 552 is the expected blood loss for someone who weighs 0. And so the question is, does that make sense? There are many times where the intercept doesn't have a meaningful interpretation. You will never perform a thyroid operation on someone who weighs 0 kilograms. Okay, so there are ways of making the intercept interpretable, in particular by subtracting the mean of all the x values, but we won't get into that right now. All right, so let's make a new prediction. So take someone who is 86 kilograms. You can see from what we've observed so far, we've only seen people up to 70 kilograms, roughly. But imagine you've got someone who's 86. What is their expected blood loss using this relationship? So we're going to plug 86 in for x, as I've done down here. So we've got the predicted blood loss equals 552 minus 1.3 times 86. Calculate that out, you get 440. Okay. So we've then now made a prediction using our inferred regression line. Okay. The rest of this goes through the interpretation of the slope, which is really critical to know. And I've already discussed that briefly. Let's continue by talking about the ANOVA table for regression. So we've seen ANOVA in a different context, where it was the experimental design was where you sample from different populations and then you're comparing the means from those separate populations, and we called that analysis of variance. And more generally, the word ANOVA is just to understand the variance of different terms in a model. And so you can actually calculate an ANOVA table for different regression models. And so I'm not going to cover the ANOVA table specifically, but I want you to be familiar with some of the terms. We've learned that the least squares line minimizes this expression, the squared differences between what we observe and what the regression line predicts. And we found that using least squares. And what we call that quantity that we're minimizing is the residual sums of squares. So let's look at some of these terms in a little more detail using a plot. So we've got our observed 5 values here. We have the regression line. And let's look at the center point and define some terms. So there's the x value of that point, and there's the y value for that point, which we're calling the response. Once you fit a regression line, the value, if you continue drawing the line up past the point or short of the point, to the regression line, that is the model fitted value. That's what's predicted from the regression line. And the difference between our response and our fitted value is called the residual. It's what's left over, or what's not explained from the regression line. The regression line is doing the best it can. And the response will not typically be on the regression line, and so this is unexplained variability, the residual. It's also called error. And we use the letter E for error to represent these values. So creating a little bit additional notation, our predicted value is this regression part here, B0 plus B1 xi. That is our predicted value. That's this right here. Okay? And so we can substitute y hat in for that part of the equation. So that is y minus y hat. It's that difference between what we observe and the predicted value that we call the error. So that's E. And so we're squaring the errors. So that's the residual sums of squares, or the sum of squared errors. Unfortunately, there's multiple names for lots of these quantities in statistics. All right. So that's our residual sums of squares. That's what we saw earlier. There's another quantity which we're already familiar with, pretty much, which is called the total sums of squares. So if we look at this quantity right here, we have y bar and yi, and we're taking the difference between yi and y bar. That's the observation and the mean. This part looks like the quantity that goes into our variance term, where we take the difference of observed value and mean, square it, add them up, and then divide by n minus 1. Well, if we don't average it by dividing by n minus 1, then that's the total sums of squares. That's the error associated with making a prediction based only on the mean. So if we use additional information than just the mean and actually fit a regression line, that amount of error is the residual sums of squares, and that will never be greater than the total. Total is the most error you can have. And effectively the regression line is explaining a little bit of trend, and that will be smaller. And that, of course, that residual sums of square can never be less than 0. All right, we're coming to a punchline shortly. All right, so the question is, how much variability in y does our regression line explain above and beyond using the mean alone? So the total sums of squares is the unexplained variability from when you only use the mean. The regression sums of squares is the, hold on a second, I need to define regression sums of squares. All right, so it's up here, regression sums of squares. All right, so total sums of squares is the amount of error when you only use the mean to make prediction. The residual sums of squares is when you use the regression model to make predictions. Therefore, what's the information that the regression line explained? It's the difference, right? There's no regression for the total, there's a regression for the residual. So the amount that decreased is the variability the regression line explains. And so that is the regression sums of squares. So regression sums of squared is the proportion of variability the regression explains. Total variability is what you got only from using the mean. That's basically a horizontal regression line. And that ratio is called R squared. It has a name called the coefficient of determination, and it is the proportion of variability explained by the regression line, specifically by a linear relationship. Let's see, do I have a plot explaining this? Unfortunately, I don't have a very good plot explaining this. All right. So one feature is when we have a simple linear regression, and if you've calculated the Pearson correlation coefficient, R, then if you square that, you get R squared. That's where the original term comes from. All right. So let's look at some two examples. So here is an example where our points, say our points lay perfectly on this line. I realize they lie slightly above, but let's assume they're exactly on this line. So our total sums of squares is the error you would get if you took the mean of y, which in this case is the number 3, and drew a horizontal line, and then calculated the distance between each point and the number 3. And use those residuals to square them, add them up. That's your total variability. Now fit the regression line. That's the diagonal line through the points. And how much error is there now? There's 0 error. And so the total minus 0 is the total. And where I'm going with this is the total sums of squared is large. The residual sums of squared is 0. Therefore, the regression sums of squares is the same as the total. We have regression divided by total. They're the same, so R squared is 1. That's a perfect correlation, and therefore the regression line explains all the variability of y given x. Page down. And so that's what we see. We see the line perfectly explaining this data. As another example, here's data that has 0 correlation, and we've plotted the mean the y equals 2.1 roughly, is the mean of y. And if you calculate all the residuals, you get the total sums of squares. Now, calculate the regression line. That happens to also be this horizontal line. And so our regression actually doesn't explain any information that the grand mean wasn't already explaining. So in this case, the correlation equals 0 and r squared equals 0. Those are the two extremes. All right, I'm going to skip by the regression of the ANOVA table for regression, and I show you how to produce that plot. I go through some discussions of some of these quantities. So we've got in our blood loss example, we have the fitted line of blood loss is 552 minus 1.3 weight. And that's the line of best fit. What's the direction of the relationship? Well, the sign for the slope is negative, so that is a negative relationship. As the x variable weight increases, we expect the y variable of blood loss to decrease. All right. Okay. So the next part is locate the analysis of variance table. I'm going to show you two ways to get this, but let's test the hypothesis of, say, the slope equal to 0. So let's let j equal 1, so that the null hypothesis is beta 1 equals 0, and we'll test that versus the alternative that the null hypothesis is not true, meaning that it's not equal to 0. So I'm going to scroll up to, I'm going to page up actually to the first table we saw here, where we fit the linear model. Let's see, yeah, that's fine. Where we fit the linear model and got the lm.blood.weight variable, and then we looked at the summary. And in this summary, we had a line in the coefficient table of weight. And here's the estimate, negative 1.3. And now we're going to do a t-test. So how do you calculate a t-statistic? You take the estimate and divide it by its standard error. So we have negative 1.3 divided by about 0.4. And so that ratio is roughly negative 3. And that's what this t-statistic is, negative 3. From there, we're going to calculate the p-value, and notice we're going to look for the values of the t-distribution that are greater than the absolute value of t. So that means more extreme in the positive direction and more extreme in the negative direction. And 3 standard deviations is pretty far out, so our p-value is pretty small at 0.02. So that's less than 0.05, if that is what we set for our type 1 error. And so we reject the null that the slope equals 0, concluding in favor of the alternative that it's not equal to 0, and probably also concluding that it's likely to be negative. All right, so now I'm going to page down. That same output is available if you ask for the ANOVA table for that linear model object instead of asking for summary. Here's weight, and we've got the degrees of freedom, which is 1. We have some different headers here. This is actually an F test instead of a T test, but you'll see that the p-value is equivalent. These are equivalent tests. So it doesn't matter which strategy you use. Typically we'll use summary and interpret that. Locate the parameter estimate table, and we're going to look at finding the, okay, that's good. All right, number 4, the r squared value. So I'm going to page up to the summary and interpret some of that information in the bottom. Okay, so here's our summary of our linear model fit, and down at the bottom we have a residual standard error. That's 11.66. That is the variability left over after you fit the regression line. We have a multiple r squared, and that's the r squared statistic that we've been discussing of almost 0.6. Okay, there's an adjusted R-squared that we'll talk about next semester. So for this semester, we'll just think about this multiple R-squared. And finally, we have an F statistic, which we're not going to worry too much about, but you'll notice that this p-value is the same as this p-value here for weight. And we'll talk more about that next semester when we discuss multiple regression. So for you, the primary information down here at the bottom is the R-squared value of 0.6. Paging down. All right. So what does that mean for 0.6 for R-squared? That means that 60% of the variability that wasn't explained by the grand mean is explained by using the regression model. And that's pretty good. What does R-squared mean in terms of how do you use R-squared? It indicates, and this is really important, it indicates the predictive ability of the model. Meaning if R-squared is very high, your model is likely to give you pretty good predictions. It is not an indication of whether your model fits the data or not. We will, in the next video, discuss model fit and how you check the assumptions of a linear regression model to make sure your model fits the data. It is possible for your model to not fit the data, yet still make decent predictions. It is also possible for your model to fit the data beautifully, but for your predictions to be lousy. So these are independent ideas, and we will learn more about that in the next video. Let me page down for a second. All right. I think we will continue in the next video discussing more about the regression model, specifically what we assume in the regression model, and then how to assess those assumptions.